9.2, solving quadratic equations by graphing. And because in 9.1 we learned about the axis of symmetry, we have a new tool that we can use to figure out, where should we really start graphing these. So what you want to remember from the previous section is that negative b over 2a is how you would get the axis of symmetry. And as a start, on this problem, I'm going to write x is equal to negative b over 2a. And I'll plug in those different values. Well, b is 6, so it'll become negative 6 over 2 times 1, which in my head I can just say that's negative 3. Setting up a xy chart, I'd like to see negative 3, but then I'd like to work my way back to negative 5, and then I'd like to work my way forward to negative 2 and negative 1. So that I'll at least get like these 5 coordinates that I think will be most important. And we'll see what ends up happening with this, and we'll see if we need to change the way we thought about it later. Let's set up a xy, labeling this as x, that is y. And I'm going to plug in these values for my table before I end up deciding what boundaries I want to use. So in my calculator, I think it would be better to type these in rather than having to kind of think about these really crazy. But if I did, I'd be like negative 5 squared is 25. Then I see this as minus 30, which puts you at negative 5 minus 7 would give me negative 12. And plug in negative 4 squared is 16, and then minus 24 is negative 8, minus 7 is negative 15. But yeah, this is a lot for the working memory, so maybe you're pulling your calculator out. This would be negative 16, negative 15, negative 12. And then when I go to graph this, I'm like, well, okay, I'm 5 back, so here's negative 5. And if I make this symmetrical, but now maybe I want to go as high as 20 and as low as negative 20. I'll let you get caught up. I'm just going to jump ahead. So that I have larger increments for 10 and then 20. Let's plot all these different points. So there is my multiple points. And as I go to graph this, this is what I was getting into in the last video. Is my graph accurate enough for the purposes I need? And really, it's not, because where the system would be solved is where y would be 0. And based on my graph alone, I can't really tell what's going on at these 2 points. So maybe, if I stretch out a little bit further in this direction or in this direction, I can kind of see what's going on. Well, 0, is a nice one to figure out. So 0 squared is nothing plus nothing, and then I get negative 7. Now I'm being careful not to get confused. This is where x is 0, which means I'm right about here. That is not where y is 0. It's where x is 0. So these have to be a little bit cautious here. Now I take 1, I'll square it, I get 1. Plus 6 times 1 is 1 plus 6 is 7. And then 7 minus 7 is 0. So that does check out. So I'm graphing this, and there's 1, 0. So I'll have a point here. So now my table is accurate enough, and I can make my graph more accurate too. Now we know that these things are symmetric. And I point that out because maybe this helps me see that I wouldn't have to keep on doing negative 6 and negative 7, because I see centered around here, I got 1, 2, 3, 4 steps, and I'm going to have 1, 2, 3, 4 steps. So instead I'll skip here and do negative 7. And then if I were to work out all the math on that, I'd get 0 over here. So based on this graph, I can put some points here. 1, comma, 0. Well, we know that they're always going to be 0 for y, and this would be negative 7. And so by graphing this, I figured out that x is either -7 or 0, where my solutions are. I'm sorry, -7 or 1, where these answers are. Now, by the end of this chapter, I think you'll find that you like this method of solving quadratics the least. Also, notice that y wasn't up here. That's because we treated y like it was 0. As a final added-on addition, let's sneak a dashed axis of symmetry here. New problem. Solve -c² plus 5c minus 4 equals 0 by graphing. Because in this problem I have a little bit more room to the right, I'd prefer that my side work ends up over here. I think the table is more central to our problem, so maybe I find the axis of symmetry by sneaking this off to the side. And when I'd simplify this, I get 5/2. Now in my head I'm telling myself this is, about 2.5. So maybe my thoughts are to go to 2, 1, and then 3 and 4. So we'll see how far that gets us. So maybe as I set this up, here's my x on the left, y on the right. And yeah, again, y is 0, but that's what we're really treating this as. We're kind of just pretending this is y equals all that stuff on the left side. And I don't like to write c and then y, so I'm going to do xy. So on the left side, if I plug in 1, maybe I leave myself some room in case I need to sneak more values up there. So here's 1, 2, 3, 4. Knowing that, this is my axis of symmetry right there. So 1 plugged in gives me -1, plus 5 gives me +4, minus 4 gives me 0. Now that's a good find. 2 squared gives me 4, make it negative, becomes -4, plus 10 gives me +6, minus 4 is 2. 3 turns into -9, plus 15 is +6, minus 4 is 2. Oh, I'm looking for patterns here. That makes sense to me, because my graph really should be symmetric exactly halfway between there and the other point. So I'm going to predict that this becomes 0. That's my prediction. So I guess I should write it in red temporarily. Now we got 4 squared gives us -16, plus 20 becomes +4, minus 4 is nothing. So my guess turned out to be correct. So when I go to graph this, here is x, y. Again, the goal is to figure out where is y equal to 0. So we'll set this up from -5 to 5, and I have 1, 2, 3, 4. Let's draw the axis of symmetry first this time. So as close as I can, and I would get rulers out for stuff like this and sketch them. It's not like I'm going to be spending 10 seconds, 20 seconds lining up the ruler. And then since my values don't go really high, I think I'm okay just going to +5 and -5 here. So let's go ahead and graph these roots first at 1, 0 and 4, 0, because I like to work on those outer boundaries. And then I can graph 2, 2, and then 3, 2. And if I really was going to use this accurately, I might even figure out what my maximum value is, because I would plug in 5/2 to get the vertex. But for our purposes, we've only been wanting to know about the roots on these problems, so we're good enough here. And so this would be my graph of y is equal to x squared y is equal to -x squared plus 5x minus 4. And I know these are all c's, but I can't imagine anybody having a problem with me doing that. There will be problems where you might want to know what the y-intercept is, and in which case I would get more accurate in this region. And I would plug in, what will y be if x is 0? But for our purposes, and I know I'm talking a lot about these, but that's just totally fine what we have. So just like the last problem, we had not one, but two roots. Not one, but two roots. Because that's where these graphs are rooted in at. So now we got what is called a double root. So let's see what happens. Just like before, I'm using the space to my side to set up negative b over 2a. But all of these have to be in standard form, which is ax squared plus bx plus c. And since this is not in that form, since I don't have 0 or just something or y on the one side, I'm going to fix that by adding 4 directly below this equation, and I'm going to write it instead in terms of y squared plus 4y plus 4 is equal to 0. Now maybe there's a party that is looking at that and you're like, wow, this would be really easy to factor. And if so, hold on to that thought. We'll look at that in a few minutes, a couple minutes. So now over here, back to the x is negative b, I'm going to write negative 4 over 2 times 1, and I get negative 2. And let's go ahead and build the table. Maybe this means that at negative 2, I'd like to walk back at least 1 and then forward 1. So if I plug negative 2 in, not to this function, but to this function, and I'll write this in red, you don't have to, just make sure you can carry along. So negative 2 squared would be 4. 4 times negative 2 would turn this into minus 8, plus 4, and that ends up being 0. So that's weird. Our x-intercept ended up being the value for y. Now I'm going to be more thorough about this than the book does, and I think it's good too. Let's go and try negative 3. So if I square negative 3, I get positive 9. 4 times negative 3 is 12. 9 minus 12 is negative 3 plus 4 would give me a positive 1. And if it's symmetric there, then the other side should be 1 as well. But these are new to us, so maybe we always show the work. Negative 1 squared becomes positive 1, minus 4, plus 4. These guys go away, so I do have 1. So there's that symmetry I was looking for. Let's graph this. Let's graph this without going all the way to 5 different points. So I'm at negative 5 back here, negative 4, negative 3, negative 2, negative 1. And I'm being back 3, up 1, back 2, right there on my y-axis, and then back 1, up 1. So this is my graph of y is equal to x squared plus 4y plus 4. I just realized I kind of screwed up here. Sorry about that. Hopefully that didn't mess you up. Those should have been x's earlier. If you caught that, I apologize. If you didn't, I guess I'm still sorry. So let's sketch out our line of symmetry at negative 2, 0. And we'll even label this as negative 2, comma 0. So for this problem, b would be negative 2 only. Now this brings up the idea of a double root. Now what this means is, this, I guess, has two solutions, but it's the same solution. And move down a little bit on your paper, and maybe do this off to the side if we're out of room. And let's rewrite the equation one more time. And above this, let's write the word factoring, because we're going to do this through factoring this time. So if I have y is equal to x squared plus 4b, dang it, 4x plus 4, well, I can factor this nicely, because this would be one of those perfect squares that work out that way. So this is the same as x plus 2 times x plus 2. And if I set the left side equal to 0, that means x would be negative 2 here and here. So that's what they mean by the whole double root thing. Now here's my opinion. I would rather solve these by factoring or some other method before graphing. I find graphing to be a little bit time consuming, but because they're good practice and they really help us see the picture, it's still something we want to do. Make this an OYO problem, and you can check it on Wolfram Alpha. Cross this out as you do this, And if you wanted to check it on Wolfram Alpha, if you just type this in, you'll get values for x. So instead of just typing that in, you might want to also type in y equals x squared minus 6x plus 9. And if you type that in, you'd be good too, because you'd get to see what the graph looked like. So this is solving by graphing using two roots.